Okay, so what types of solids can we find the volumes for? If you think of some solids you've encountered in your life, what's a solid that you know there's a formula for?
A cube.
Cube, definitely. Yep, yep, I agree with that.
Um, a sphere.
Sphere, sure. That's right, Clea. Cylinder, that's right, Javier. And so yeah, these are some solids that there are formulas for. And you know, in like you see there on the screen there, in trying section 6.2, in trying to find the volume of a solid, it's similar type problem as finding areas. We have an intuitive idea of what volume means, but we need to use calculus to give the exact definition of volume. So indeed, in figure 1, these are some very common solids that we know formulas for. Okay, they don't have the sphere there, but there's a formula for the volume of the sphere. But we want to have a formula that can find volume for a general set of solids. Okay, we want to have a procedure, I should say. So what we can do, if we go to figure 2 here, we look at this figure, you see a solid. You see this solid S. And the solid S goes from x equals A to x equals B. This is figure 2 in section 6.2. And if we were to make a cut in the solid, okay, then the cut itself would look well, for that value of x where they're making the cut, um, there's a cross-sectional area, that purple cross-sectional area, A sub x. And that cross-sectional area of the cut there is a function of x, because I think you can understand that if we were to cut the solid in different places for different values of x, the cross sections are going to look different, and so the areas of the cross sections are going to be different, and that's why the area of the cross sectional area varies as x increases from A to B. So that cross sectional area A has to be a function of x. Okay, are there any questions so far? All right, well then let's proceed on, because we want to get to volumes now. We want to get to volumes. So, okay, well, in figure 3, okay, what we're doing here is we are taking the solid and we're looking at a slab or a slice of the solid. The slice of the solid has width, so in figure 3, the picture to the left, that slice has width delta x. Think of it like a loaf of bread, a slice of bread. That slice has width delta x and cross-sectional area A of x. Okay, and of course, we can take the loaf, we can take the solid, and we can cut it up into a bunch of slices or slabs and get what you see there in figure 3 on the right, an approximation of the volume of the solid.
Professor,
Yes, yes.
is this like when we did the graphs and we did the rectangles to find the area?
Well, Yeah, it's an extension of that in 3 dimensions, basically.
Mm-hmm.
But yes, it is a similar uh, uh, procedure. Indeed, indeed. That's right, Clea. And you see there, now how would we approximate the volume of that solid there in the left of figure 3? Well, we would add up the volumes of all the slices. Well, what's the volume of the slice? Well, if we take the area of the ith slice there in figure 3 and multiply by the width of that slice, that would give us the area. So the volume, hold on here, the volume of the ith slice is approximately equal to the cross-sectional area of that slice, that's a function of x, times the width, which is delta x. Okay, are there any questions so far? Okay, okay, well, so if we want the full volume then, the full volume, we have to add up the volumes of every slice. So that is a Riemann sum. As I goes from 1 to n, the volume is approximately equal to that sum. The volume is approximately equal to that sum. Now, how can the sum be a more accurate approximation of the volume? What do we have to let n approach?
Limit?
That's right, the limit as n goes to infinity. The approximation would be better and better as n approaches infinity. Okay, and so like to sort of see that, if you wanted like to see a little idea of that, in the next problem where they talk about a sphere in figure 5, they show like where you have these, cylinders are the same as, well, they're using discs, but they're taking slices, but then the slices are essentially discs. And you can see the more discs you use, the more slices you use, the better the approximation is going to be to the volume. So there's no question that if we take this volume and we let n goes to infinity, let n go to infinity, we're going to have then a formula for the actual volume. Absolutely amazing. Let S be a solid that lies between the limits x equals a and x equals b. If the cross-sectional area is a of x, then the volume is the integral from a to b of a of x dx. And so now you have, I mean, it's really quite amazing. Now you have a way to find the volume of a solid. And for instance, like a sphere, you can prove the formula for the volume of a sphere using this formula. They show that in example 1. Okay, but I think I'd like to move to example 2 and look at another example. So let's go to example 2. Are there any questions? Are we good? Maybe give me a thumbs up if you're feeling okay so far with this material. Okay, Clay is good. And Susanna's good. All right. Liliana, wonderful. Good. All right. Gabriel, how do you feel? You good? Wonderful, wonderful. Okay. OPME, how about you? Good. Okay. Wonderful, wonderful. Well, So let's get to a little example here. So let's go to example 2. And they talk about, we have to have a way to define these slices. And so there's a method called the disk method. And in this example 2, what they want you to do is they want you to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals the square root of x from 0 to 1. Okay, so, okay, well, let's go ahead and get an idea of what this volume looks like. So we're taking the function y equals the square root of x and rotating it about the x-axis. So here in figure 6, okay, there's the function y equals the square root of x, and you are limiting that function between 0 and 1, and you're taking that blue region and you're rotating it about the x-axis, like a rotisserie chicken, right? How many have seen those in the stores? How they rotate about an axis? Okay, Leah knows what I'm talking about, and Daniel knows, and Avery, and so okay, and OPME, and so this is what this is what the solid's going to look like in figure 6 and in the second graph. Now that is not a half of a sphere. Okay, that is not half of a sphere. That shape is like a bowl. It's like a bowl, and we want to find the volume of that bowl. So how would we find the volume of the bowl? Well, we can slice the bowl up, take slices of the bowl. What would the slice look like? Well, it looks like a disc, looks like a cylinder. Okay, it looks like a cylinder. So do you see there in the second picture, a slice of that solid looks like a cylinder. Now the cylinder has length delta x, and let's see. Now to find a volume of a cylinder, is pi times, well, what's the formula for the volume of a cylinder? Do you remember? Well, we got to take so Susanna, pi r squared will give us the area on, like, if that purple cylinder there in the picture. We're getting a little closer. We don't quite have the right answer yet. Good.
We need also the height.
Right. Well, what would the height be on that cylinder there in the picture?
Well, the height. Well, just
Square root of
the height.
x.
Well, I'm talking just that purple cylinder. Shalom and Clay and everybody, just that disc, the purple disc. Okay, delta x is the width, and
Won't
then
it be
what's
the integral?
radius? I'm sorry, Opiemi?
Won't it be like the integral of square root of x?
Well, we're going to get there, but I'm just wondering what the volume is of that purple cylinder there in the picture in figure 6. The width is delta x, and the area of the cylinder has volume pi times r squared times h. Pi times the radius squared times the height. How many recall that formula for the volume of a cylinder? Or does that kind of ring a bell, so to speak? Okay, so Clay and Shalom and Avery have seen that, and so the height of this cylinder, it's sideways, but it's delta x. But what's the radius? What's the radius of that purple cylinder? If you look at both pictures there. What would
So
the
are we
radius
talking
of?
about the radius now or the height?
Now we're talking the radius.
Oh,
What's the radius of that cylinder? That's right, Nihat. Square root of x. Square root of x. So you see in figure 6, the first picture, we're rotating that region about the x-axis. For every value of x, that region, I mean, if you think about that region, okay, think about that like in the first picture there where x is, the height or the height of the function is square root of x, right, at x, because y equals square root of x. So if we rotate that square root of x, that, like, think of rotating that purple line segment about the x-axis, you're going to get the disk or cylinder below. So the volume of this cylinder would have to be pi times the square root of x squared times delta x. Okay, so in other words, the cylinder has area on top, pi times r squared. That's going to be the cross-sectional area of that cylinder is pi times delta x squared. That's your cross-sectional area, which is pi times x. The volume then, the volume is going to have to be the area times delta x. So that's pi x times delta x. So does this make sense based on figure 6? What you're, if you, there's figure 6. And then if we, you can see the radius is the square root of x. So the cross-sectional area of that cylinder, right at the top of the cylinder, is pi times the square root of x squared. And then the width is delta x. Okay, the width is delta x. And so now the volume then is pi times square root of x squared times delta x, which is pi times x times delta x. And now we know what a of x is. So here is the volume. The limits go from 0 to 1. So it's the integral from 0 to 1 of ax dx. So that's the integral from 0 to 1 of pi x dx. The volume of that solid, of that bowl, is equal to pi divided by 2. That's the exact volume, pi divided by 2. So if we're talking, inches, it's pi divided by 2 cubic inches. If we're talking feet, it's pi divided by 2 cubic feet. So is it valuable, you think, to be able to find the exact volume of that bowl there in figure 6? If you're a company that has containers in that shape and you're putting like, I don't know, pudding in there or something. All right, Clea sees the value. You'd want to know the exact volume of your pudding. I mean, if you're making a 100 million little containers of pudding, if you're off a little bit on how much pudding is each container, that could be big bucks, So finding the exact volume is very helpful. How many think this is kind of cool, what you're learning here in section 6.2? Okay, Susanna's liking it. Liliana, Clea, Mark, Nihat, wonderful, wonderful. I like to try to say names of people who are replying, just because it shows it's like giving you credit for your response. So now this is a very simple example of finding the volumes of a solid. We're gonna next week on Monday, we will be doing more examples, but at least now we've touched upon this. Are there any questions on this section 6.2 so far? Okay, well then I will stop the recording. One moment. Stop the recording here.